What?
The camera. The video camera.
That'd be fine too.
The new one.
I don't know, just the mic never ready, so I grabbed it.
It doesn't have autofocus.
If you have enough space in the car.
I'm not going to be tap dancing. So. Okay, should we get started?
Yeah.
Okay, so this is the fiber reinforced polymer, or FRP, construction seminar. You guys probably know me, I'm Ivor. And we're going to do this 3 days. Some of you are only going to come for the first day. And we're going to have a lecture today. It's going to last probably a little more than 2 hours, maybe a little less. I don't actually know. I haven't tried this before. We're going to talk about the theory of composites and fiber reinforced polymers. Tomorrow, if you want to participate, we're going to build some test samples, and that'll be the longest day. We're going to need to come in right after lunch. I probably work right until about a week, because especially with this many people, we're going to work in groups of 2, and we're going to build little test samples that I'll describe at the end of this lecture, and then we'll break them. You can see who has the best workmanship, and maybe get a little bit of data on what beginners actually, what kind of strength levels they actually get when they make things out of carbon fiber or resin. And the third day, we're going to have to cut and trim the samples and put them into a little test fixture that I set up a few days ago. I'm putting some things in yellow, the warning, which just means like it's not going to kill you, but it might break the part that you're working on, or it might not be good in general. And things that are danger in red, please pay attention to those because they can hurt you. So some of the materials in carbon fiber reinforced polymers are carcinogenic and dangerous, and you should make sure you throw away them properly, dispose of them properly, and you don't, drink the resin or something like that.
How would you define appropriate clothes?
Generally, for tomorrow, we're not going to be doing anything especially dangerous in here. I'm going to say closed shoes. Just no sandals and long pants would be fine, and a t-shirt would be fine. You don't need to have long sleeve shirts or anything like that. But if you get any resin on it, it's never coming off.
Yeah.
So it's more for don't bring a nice collared shirt in and expect to stay perfectly clean. It's pretty hard to not get 1 or 2 drops on your clothes if you've never done it before. Now we'll work carefully. So today we're going to cover 7 different sections. We're going to talk about how composites work and a little bit of the theory behind them. Very little of the theory, mostly just sort of an intuitive, practical understanding, because that's mostly my understanding. I'm not a professional in this subject. We'll talk about the materials and fibers and fabrics, resins and bonding, and core materials. We're going to be talking mostly about sandwich construction. We're not going to be talking especially about just the carbon fiber and resin. So for example, I've got a bunch of test samples that we can pass around here, and if you have just like 1 layer of carbon fiber, it's actually quite flexible. And if you build it up to 3 layers, it starts to get stronger, but you can still break it. However, those same 3 layers, when put over a 100-volt core, become much more rigid. This is a construction method that's very often used in aircraft. Home-built aircraft, and a lot of the techniques I'm going to describe today are from the home-built aircraft community. So I guess we can pass these around a little bit later when we get to the actual sections. Then we'll talk about some amateur design tips. I built this robot, Jimmy, here at IIT. It's made of fiberglass and foam on the top, and expanding polyurethane foam and carbon fiber on the lower half, and the whole carbon fiber and structure weighs about 1 kilogram, a little less. The aluminum weighs like 6-7 kilograms, so the aluminum in motors are much heavier than anything that was made by me. And using this stuff that I'm going to describe today, you can build something like this here at IIT. And finally, we'll talk about the construction methods: wet layup, vacuum bag layup, moldless layup, and molded parts. And then we'll talk about the construction tutorial tomorrow. Okay? Any questions before I get started about the... Okay. So, brief history. Glass fibers have been around for more than 100 years. There was a World's Fair entry where some woman wore a dress made of glass fibers. And they began to be studied more after the turn of the century when people were studying crack propagation in materials. A British engineer was pulling rods of glass, increasingly thin, and noticing that the thinner he pulled the glass, the stronger it was. There had been a computation done from chemistry and physics that said that glass should be much stronger than steel, but obviously when you took window glass and pulled on it, it wasn't nearly as strong as steel. They were trying to figure out why this discrepancy occurred. And the theory is that the macro properties of glass are different from the micro properties because there's a longer relative distance between flaws in the glass, little flaws that cause a crack or breaking of the fiber. So we're able to make thin fibers of glass more precisely than we are plate glass, and it's almost the same stuff as in windows, in fact. But we didn't have a way to hold the fibers together until usually about, I would say, the 1950s. Before that, there was only a few hobbyist people actually doing fiber-reinforced plastics. And the thing that we use today to hold fibers together is a type of plastic. It's a polyester, vinyl ester, or epoxy resin. And those became commercially feasible in the 1950s. Later on, people started looking for even stronger fibers. The carbon and aramid fibers took off commercially in the 1970s. And now you see carbon fiber and fiber-reinforced polymers in bathtub, surfboards, boats, housing insulation, aircraft, cars, wind turbine blades, body armor, spacecraft, the list goes on. It's a very common material now. So composites work a lot like reinforced concrete, plywood, or even metal alloys because you essentially combine two materials to form a stronger structure. In particular, we're using fibers or long, skinny things with a lot of with good tensile strength, and we bind them together with another material that has a high compressive strength. So concrete uses steel rods and Portland cement. Plywood is using glue and fibers stitched in different directions, and alloy metal using two different crystal structures. For the things that we're going to talk about today, the matrix is almost always more elastic than the fibers. And what that means is the resin matrix that holds the fibers in their orientation is going to deflect a little bit, and the fibers are going to be carrying most of the load. And we'll see in a couple more slides what that actually means. So the matrix only has to carry the fibers the load a very short distance before it comes in contact with the fiber, and then the fiber will be stiff enough to carry the load without bending. Usually the fibers are 10 or 100 times stronger than the matrix. So here we can see I believe this is boron or silicon. Sorry, boron or yeah. Anyway, some type of metal fiber embedded in a matrix of resin. You can see all the fibers going in the same direction. We want as little resin matrix as possible when connecting the fibers. We want to wet the fibers out. We want them to be completely connected with the resin, but we don't want any extra. We want the very minimum that we need. So the closer these fibers are together, the stiffer the part's going to be because the resin matrix is more flexible. The weaker the part is going to be if you have extra resin, and the heavier it's going to be because if you have extra resin. So the better construction methods use autoclaves, high temperature ovens, a lot of pressure to squeeze out all the extra resin that they can. And depending on the type of fabric, that might be 20 to 50%. Unidirectional fibers usually use less resin than the bidirectional weave, the cloth weaves like this that we're going to use. So the strength characteristics are very anisotropic. We have, in the direction that the fibers are running, these materials are very, very strong. In the other direction, they're not strong at all. So the material is fundamentally different from metals and crystals and things that we're normally used to in engineering. I've read a paper where they described it the strength as the cosine to the fourth power between the direction of the load and the direction of the fiber orientation. So you get full strength of the fibers if the load is in the direction of the fibers. This is a fiber and you're pulling that way. full strength. If you're pulling at an angle and the load is this way, you're going to have increasing, the strength is going to drop off pretty quickly. So the tensile strength of a resin, it might be 50 megapascals and has a density slightly more than water. The fibers will be, say for carbon fiber, might be 5 gigapascals and a little bit heavier. Steel is 800 megapascals and about 8 kilograms, or 8 grams per cubic centimeter. So you can see that this stuff is much stronger than steel by weight. In the direction of the fibers. In other directions, it may not be as strong, and an isotropic structure made of this may not be much stronger than steel. It may be a little bit stronger than steel, or have a better specific strength. So the specific strength here, for example, these are some elastic moduluses and the specific tensile strength, so the strength divided by the density. Here are the metals, aluminum, titanium, steel, magnesium. You can see that glass can actually be much stronger, fiberglass, and epoxy and graphite can be pretty strong, but you can actually have some fiberglasses that are stronger than graphite or carbon fiber. By the way, graphite and carbon fiber are the same thing, they're just named differently for historical reasons. So the thing that everyone likes about carbon fiber and graphite is that it can get very, very stiff. And so you can make extremely rigid structures very, very light, even if it's not as strong as some of the fiberglasses. Go ahead.
There's a question. When you said the load must be applied in the direction of the fiber, which kind of load? Tensile, compression load, or flexion?
Flexion loads, a fiber will bend if you flex it. You have to put it in a tension or compression mode generally.
Okay.
We'll talk about the different types of loading a little later in the course, but generally almost all the strength is along the direction of the fiber. This course we're going to talk about monocoque. Does anyone speak French? Am I saying that right? It's from the French word coque, from shell, so a single shell structure. And FRPs are generally used in these monocoque structures. They have a load-carrying skin. So whereas with metal, we make a truss structure and we compute the forces and everything at each joint, with a monocoque structure, we create a skin that carries all the load, and we create as many compound curves on that skin as we can to make it stiff and rigid, and we bolt things directly to that. So whereas this was made from many small pieces, this is all just one big piece with maybe a couple of attachments attached to it. So the benefits, you can make something really light and strong and stiff. This can actually be stiffer than that, surprisingly. You can replace a lot of smaller parts with one molded part, but it's generally more difficult to work on after you've built it. You can't embed metal as easily after you've built the thing. You can't machine it very well after it's been built. It doesn't handle stress concentrations as well as metal does, so you can't just strap on things afterwards. You have to kind of design it more up front. And it's more difficult to mass produce because the process of putting fibers and fabric down on a mold is a labor-intensive process that currently humans do it. We don't automate it very well. There's some chopped gun robots that shoot out fibers, but not very many. So if we're making a really thin structure, if we're making a load-carrying skin, how do we keep it from buckling or being really floppy? If you were to take a regular classic beam, apply a load at the end, and look at the internal stressing, we see there's a lot of tension in the top surface, a lot of compression in the bottom surface, and in the middle there's some amount of tension or compression smaller than that. If, however, we had a core, and the core has enough shear strength and the compressive strength to keep the two surfaces apart, you end up with very little loading in the core because it's a little more flexible than the surface material, and you have all of the tension and compression loads in there. So you're using the fiber much more effectively. Instead of having just this heavier fiber in the center and just a little bit on the surfaces carrying things, you can make you can more effectively use the carbon fiber material. So the core materials only have shear loading, but they are structural, as we'll see. Here's 3 core materials that I've been using here at IIT. This is honeycomb, this is a PVC foam, and this is a polystyrene foam. We'll talk more about those in a second. I'm going to just start passing this stuff around so you guys can look at it. Here's some core materials. This is a Nomex honeycomb, which is commonly used in aircraft manufacturing. It's an aramid, much like Kevlar. This is some fiberglass samples, 1, 2, and 3 plies. We have some Kevlar, which has a nice yellow color. Very tough stuff, impossible to cut. And we have some carbon fiber. Be careful with this. I take the edges so the fiber shouldn't get out, but you could probably mess it up if you tried. This is the cord composite piece with styrofoam on the inside. It's labeled. And some regular carbon fiber samples. And this is a polyurethane resin, which I also poured here. This is an expanding foam, so it's a liquid. You pour it into a mold and it expands. We're going to talk about all these samples in a little bit. Okay, so glass fibers. The most common type of fiber reinforced polymer is fiberglass. And glass fibers are usually about 5 to 25 micrometers in diameter, and they're made of silicates, just like regular window glass. They could be pure crystalline SiO2, silicon dioxide, and you get these great quartz crystals. But the temperature required to make those crystals and the time, it's more difficult, so people add other silicates, or they add other materials like aluminum, calcium, magnesium to the glass to get it to cool at a lower temperature, and the strength is reduced, but not substantially. And then you get these amorphous glass structures. I don't know much about chemistry, but I think some of these type of molecular diagrams are interesting because the fundamental material strength of all these materials, of the glues, of the fibers, everything relies on long molecular chains with some cross-linking between the molecular chains to create a strong material. So the three types of glass that are commonly used are called E-glass, C-glass, and S-glass. Most people are going to be using E-glass, which is the most common. You buy that at the boat store or anything like that. Or S-glass for strength. E-glass is electrical, C is chemical, and S is for strength. The S-glasses are about maybe 20%, 30% stronger than the E-glasses, and are often used for structural application. You can also make different blends of glasses if you want, which have higher elasticity, radiation shielding, sometimes they use lead in them. They have different glass fibers for fiber optics and light transmission. The next most common material is probably carbon fiber, especially in the last 10 years. People are just loving carbon fiber because it's got that great black color, I think, more than anything. It looks cool. Which comes from 2 different manufacturing processes. One is from polyacrylonitrile, or rayon, and it's a carbonization process. So they take some smaller molecules, heat them up, and then they start to form these long chains. I believe this is brand a synthetic molecule. It was invented in 1958, but it wasn't really commercially successful until about 10, 20 years later. The other way to make carbon fibers is from petroleum or tar pitch, also by carbonizing it, I believe. And you can sort of customize the carbon fiber a little more to have the material that you want. They can be customized to have zero thermal expansion, so they're nice for dimensionally accurate parts, such as in jet engines. You can have higher electrical conductivity or heat conductivity. In fact, those two often go together. And much higher thicknesses than with the pan fibers. Carbon fibers are sometimes called graphite, especially when they've been heat treated after production for additional strength. And you can have up to about maybe 6 gigapascals of tensile strength. The fibers are about 5 micrometers in diameter, and these fibers can be about 5 times as stiff as glass, as fiberglass. As I just said, The stiffness, thermal, and electrical conductivity often go together. As you increase one, they'll go together. This is not true for the resins. The resins do not conduct electricity. The resins do not conduct heat very well. They're just plastics. Aramids. So the aromatic polyamides are a synthetic family of fibers, and they include Kevlar, Nomex, Vectran, etc., etc. They were invented by Stephanie Kwolek at DuPont, who produces the vast majority of these fibers nowadays. They're extremely tough, and if you try to cut some of this, if you ever try to cut Kevlar with regular scissors, it's incredibly frustrating because when you cut with the scissors, the fibers just kind of bend around the fiber. It's really amazing stuff. So even the tensile strength can be as high as fiberglass. It can be a little stiffer than fiberglass. It's not as stiff as carbon fiber, but as for robustness goes, this is a really great material. It's non-conductive. It doesn't have a melting point. It starts to degrade. It's more resistant to fire than some of the other fibers. It has really great abrasion resistance, and but you do need to use an epoxy resin rather than the polyester vinyl ester resins, which I think I'll talk about next. Oh no, one more thing. There are of course other fibers. You can use metal fibers like boron, aluminum, titanium, silicon carbide. You can use Dyneema or Spectra, which I think I figured it out. Which is a very large molecular weight polyethylene material. However, that's not used much in fiber reinforced polymers because we can't glue it very well, as I understand it. Maybe they're working on that. They can use some Spectra fibers for body armor and stuff like that, but it's not widespread yet. And in the near future, we'll probably see carbon nanotubes and other carbon-based products being the highest strength materials because of carbon's unique position on the periodic table. It's got a low molecular weight, a lot of free electron orbitals to bond strongly with other things. So when you get the fibers, they come in a bunch of different forms. They can come in big roving spools like this, which you can then chop up and spray with a gun and some resin, like when they make a bathtub or a boat and they want to build up the structure. They have this sort of chopping gun and they just kind of spray on the fibers and then they cure in an isodirectional manner. That usually is a bit heavier than and doesn't use the best, doesn't make use of the materials in the best way. So another more useful way for, I guess, for robotics and aeronautics is to use unidirectional fibers. These little white cross stitches are there just to sort of hold the fibers in the right direction, but 99% of the fibers are running in the north, up-down direction here. And if you want to get strength in different directions, you just start stacking unidirectional fabric, storing fibers this way, this way, this way. And if you do that a few times, it starts to approximate an isotropic material. More common for us, we're going to, yeah, go ahead.
In the test plate that you show us, when there was the fiber cover 1 layer, 2 layer, 3 layer, the layers are put in the same direction or
in these, I put all of the fibers in the same direction, yes. When we make the test samples, we will make one test sample which is at 45 degrees so we can see what the effect of...
it become more stronger.
It'll become strong in a different direction.
In different direction.
Yes, exactly. So we're going to use mostly bidirectionally woven fabric, which means some of the fibers are going this way and the other ones are going 90 degrees to that. And there's a bunch of different weaves. If you ask any, did you break something? No.
You're right. Yes. What does it mean?
It's if you want to, here's one that's broken. You can see.
You can broke this.
I took this actually and broke it a few different times because I was curious to see what would happen if we broke something with just one layer thick. And the most common failure for the stuff we're going to make today, in my opinion, is going to be when the FRP is going to pull off of the core material. So if you look at that, you can see that the carbon fibers did not stick very well to the honeycomb because I didn't do that piece in a vacuum bag. There wasn't sufficient pressure, and the bond wasn't very strong between the core and the surface. And that just totally makes the part. It starts off really, really stiff. I mean, if you compare that piece which is after it broke, and this piece, which is before it broke, is totally different. So, anyway, back to the fibers. So, just like cloth fabrics produced for shirts and everything like that, we can have a whole bunch of different weaves of fabric for different purposes. The most common is just the plain weave, where you go over one bundle of fibers, under one bundle of fibers, over one bundle of fibers, kind of like this, over here in the corner. Or basket weave, where you have sort of two groups of fibers going together in the same over and under pattern. Then you just get into the twill and the crowfoot weaves. This is what they're called in English. I don't know what they're called in other languages. Where it goes over two and under two, over two and under two, and it has a sort of different texture. And then finally the satin weaves, where it may go over one and under a bunch, like 5 or 8, and come over one and under one. And why do we have all these different weaves? Generally, the looser the weave is, the higher the strength will be, because you can, the more of the fibers will be running in the direction that you want it to. So this weave, they're kind of going up and down a little bit in the fibers, but in the satin weaves, there's this long space here where all the fibers are running in exactly the direction you want. So they can be stressed more highly, and you can drape these types of cloths, the satins, over compound curved surfaces, over surfaces with curves in two directions more easily. On the other hand, they're more difficult to work with, and they unravel more easily. So when you're actually building stuff, they're a bit more pain in the ass than the plain or basket weaves. And sometimes you'll see stuff like 3K or 3K or 24K, which means that refers to the number of fibers, of carbon fibers in each little bundle. So fibers can be dangerous. There's evidence that many of the synthetic fibers, fiberglass, Kevlar, carbon fiber, are carcinogenic, especially when you get them in the lungs. They can, some people are more sensitive than others, but you don't want to find out that it's you, so please don't ignore this. Especially when you're cutting, grinding, or sanding these fibers, you should always wear a mask, at least a dust mask, preferably one with the can dust mask, which have a finer particle tolerance. So on Thursday, when we cut things, we're going to just be using sharp knives, because I don't have good materials for cutting and grinding, and the thickness of the parts that we're going to be making can be cut with a knife and some patience, and that makes almost no dust. And we'll do this outside anyway, so it'll be fine. Other things to consider about fibers: when you handle them, the dirt and oils on your hand can get on the fibers and decrease the strength. Now this is all best practice type of stuff. You can use carbon fiber and handle it with your hands. It doesn't really matter so much if you don't care about making aerospace or super high quality parts. But you should know about this, because you don't want to have dust and stuff on your fibers if you can avoid it. The fiber and the resins also absorb a lot of moisture from the air, and so ideally you keep them in an elevated temperature prior to actually doing your bonding, to let all of the moisture that is accumulated in the resin or the fibers gas off, so that you have fewer bubbles in your resin when you actually do it in a vacuum bag, as we'll talk about in a second. The more you handle the fabric, the more you're going to disturb the weave and decrease the strength of the part. And the fiber should always be oriented in the direction that you want to carry the load. Resins. So the other part of fiber reinforced polymers is the resin matrix. And it's a plastic, also known as a polymer. And resins have about 5 things that you need to consider. You need to consider the adhesive strength, how well the resin sticks to the fibers, the cohesive strength, how well the resin sticks to itself, wettability. Some resins are more viscous than others and will wet out the fibers more easily at lower pressures and temperatures. The activity of the resin and how the chemistry of the fibers and the resins match, and how well the resin will resist degradation, how stable it is over time in an environmental effect. So as I was saying earlier, the tensile strength of the fibers are much, much higher than the resin. And you kind of want to imagine yourself that when you're taking this fabric, you're embedding some sort of really strong tensile strength material, like a steel cable, in a plastic. And the surface area of the fibers is going to have as many as much surface area on those fibers. Here, try it again. So most people in the composite industry call these resin systems because the resins aren't just for gluing the fibers together. In fact, you have a lot of things you need to glue with the resins. You have to glue the not just the uncured fibers, but the cured pieces together. Sometimes you need to mix in some little glass spheres called microballoons or microbubbles in with the resin to make it lower density, to make it more like a paste instead of having it be like a glue. Sometimes you need to glue or embed metal in your composite piece, and so you need to have something. Your resin needs to bond well with the metal. You need to paint your surfaces when you're done, unless you prefer just the straight carbon fiber look. Even then, you often need ultraviolet protection. You need to add some protection from the ultraviolet rays, which will damage your resin quite often. The resin will degrade if left in the sun. And you also may need to make the resin impermeable to certain chemicals, fuel, etc. So your resin chemistry must match all of these, and unless you're a chemist and know what you're doing, you should try to follow one resin system from one supplier. Make sure that your paint is from the same supplier that your resin is from, and that your microballoons and everything, you should just buy it from one supplier, and it'll all work out more easily for you. Same thing for waxes and stuff like that. So the three resins, and I've already mentioned their names, but now I'm going to explain it a little better. The most commonly used one are the polyester resins. The polyester resin cures in a big molecular chain all by itself. They're little small molecules that bond to form long chains, which provide the epoxy resin with strength. And the hardener is just needed to start the reaction. There's a catalyst that's needed, but because of this, once the resin starts to cure, you don't need the hardener as much anymore, and you have a good tolerance for error in mixing. Typically, when you make polyester resin, you'll mix up 1 or 2% hardener relative to the amount of resin, and polyester resin is really cheap, has okay strength, but it shrinks a little bit when you, as it cures, it shrinks by a couple of %, which means if you're trying to make a mold, or if you're trying to make something dimensionally accurate, when you use polyester or even vinyl ester resin, it'll shrink and your part will become bent or the wrong shape. For that reason, I've only been using epoxy in robotics and boat building and all that kind of stuff. Simply because the polyester and vinyl ester resins probably are not suitable for the really high precision stuff that we want to do. If you're making a low precision boat or bathtub or something like that, go ahead and use the polyester. And if you're making a really big boat, maybe vinyl ester is okay. It's a lot cheaper. But for the small quantity stuff, you just save yourself a headache and go with epoxy. So vinyl ester resin has lower viscosity, which makes it a bit easier to wet out the fibers in fabric when you're working with it. And epoxy resin, on the other hand, unlike the other two, has a different type of chemistry. There has to be A molecules that have to find a B molecule and come together to form a strong material. So you might imagine that this long molecule is the A molecule, this long one is the B molecule, and they form little cross links there to form a strong molecule. If you don't have the right ratio of A molecules to B molecules, it never gets harder, and it's gummy forever, and your part is ruined. So be very careful to mix epoxies in the right ratios. Use a mass balance or a very high precision epoxy dispensing equipment and mix it thoroughly before you start, or you'll have something that is never going to cure. And once it's kind of half cured, you can't do anything about it. Epoxy sticks to a lot more materials than polyester resin, and often doesn't affect certain foams, as we'll see. The resin hardness can be measured pretty easily with little handheld tools, and you can tell based on the hardness of the resin how well it is cured by comparing it with the data sheet, for example. Resins can be dangerous. Danger, danger, danger. Some chemicals and resins can penetrate the skin. Now this is mostly true for older resins, but if you don't know what kind of resin you're using, you should always be careful. In the past, people who weren't careful developed skin irritations, even blindness, can have cancer from handling these chemicals with your hands. So please wear gloves and avoid contact with your skin. The hardener is typically more reactive than the resin. So in the epoxies you'll have, or the vinyl esters, you'll have two materials that you're working with. Usually the hardener is the more reactive of the two. For example, in polyester and vinyl ester resins, they often use methyl ethyl ketone peroxide, MEKP, which is a promoter, and it's highly poisonous, and it's also a high explosive. It explodes at 5 kilometers per second or something like that. You'll use the stuff you get with the epoxy resin systems, or sorry, with the in a kit when you're actually making a vinyl or polyester resin, it's diluted to maybe 20–30%, I believe, so it won't explode immediately, but it's pretty reactive stuff. You want to treat it with care. Another thing you want to think about is the curing reactions as this glue hardens are exothermic and they're releasing heat. So when you're making a batch of room temperature epoxy and you mix the A and the B, if you're mixing more than a few hundred milliliters and the cup is, say, a plastic cup, the heat generated by the curing as it starts in the cup can set a fire, can start a fire. Now generally, when you're working with it, you're painting it out on a big surface. There's plenty of things for plenty of time for the heat to dissipate, and you need that heat for the epoxy to cure in all. That reaction has to take place. But on a hot day, outside with a big batch of resin in a cup that you leave for 5 or 10 minutes, it can start a fire. So don't mix 2 liters of epoxy together, room temperature epoxy together at the same time. Some epoxies require higher temperatures to cure, and you can mix those in big batches, and that's fine. It's a different material. But the stuff you're going to buy at the boat store, just be aware. Finally, if you don't know what you're doing, also just use soap and water for washing the resin off your skin. It takes a lot of soap and water, but don't use any solvents because sometimes you don't know what the chemistry is, and it can help the resin penetrate your skin more easily if you use certain solvents or others. So, now that the warnings are out of the way, or the dangers are out of the way, we can get to other considerations about resins. Strength depends on many factors. Handmade parts can be about 5 times weaker than an industrially made, properly process-controlled part, even though the materials are essentially exactly the same. One of the reasons this is possible is because professional shops can use high temperatures and high pressures. High pressures can help make a part stronger by reducing the resin content, by squeezing out all that unneeded resin. The high temperatures can help by making sure that all of the epoxy A molecules meet with the epoxy B molecules, and they can find their bonding pairs, so you get a perfect cure of the epoxy resin. Even for amateurs, after your resin is cured once, you can do post-curing, which is where you increase the temperature by about 20 degrees above the temperature that it originally cured at. And holding it at that temperature for 4 to 8 hours can make it a little bit stronger. It can just guarantee that all of your epoxy molecules have properly bonded. Another consideration we're going to talk about more in the design section is shear loading your fabric is generally not a good idea. I mean, if you're thinking of that sort of cutting scissors-like action on your fibers, fibers can be about, I mean, the strength is about half of the tensile or compressive strength. So shear loads are not something that fiber reinforced polymers excel at handling. And finally, I guess once resins have cured, they're just generally plastics and are reasonably safe to handle. Couple more warnings.
Just a question.
Sure, go ahead.
How can you cut them if the shear load, shear strength is just half of the tensile strength? That is 60 gigapascal. I mean, it's a huge event. Cut them.
When you're using scissors, it's pretty easy to cut. Carbon fiber is the easiest actually to cut with scissors. Then I would say fiberglass can be cut with scissors, and finally Kevlar is, you need really nice quality big shears to cut, or you need a special roll. The fabric, before it's cured, is pretty easy to cut. After it's cured, you're going to need a knife, and you're going to need to start scoring it a few times with the knife, and then maybe crack it and break it. When I talk about shear, you don't want to shear load it. I'm talking about it from the design perspective. So probably that should not be on this slide. That should be on a different slide later in the presentation. Anything else? Questions so far? So the vinyl ester and polyester resins contain some styrene. If you're working with styrene foams, like this blue one, polystyrene, now you can dissolve the foam, which is a nasty surprise when you're trying to make something out of two materials. So that's another reason I say just use epoxies all the time, because the epoxy doesn't dissolve the foam and then you don't have a problem. And as I said earlier, the polyester and vinyl ester resins shrink by a couple percent during the cure. Yeah.
What if you need to make a curved shape?
What kind of curved shape?
Yeah, I show you. Because you have some foams which are pretty stiff.
Yes.
So how can you?
We'll talk about shaping foams a little bit later. So the cores that we're going to talk about in this course are used mostly with light aircraft, home-built aircraft, which is where I'm getting most of my information. So polystyrene, styrofoam, the blue or white colored foam that most people are familiar with. I actually passed around this white colored foam. This is an expanded bead foam, I believe. I'm not sure what kind this is, but this is not the right kind of foam to use in construction. I passed it around as a sample, but this white foam has open cells, which means if you were to get this wet, the water could go all the way through it. And you generally want a closed cell foam, like this or this, which does not allow water to penetrate or resin to penetrate very far. It'll have better structural properties and is more useful for construction. So this is this would be the polystyrene, this would be polyurethane, this is the syntactic, and this is just balsa wood, which can also be a great core. So the yellow polyurethane foam is brown in color. You can get pre-expanded 1 or 2 part liquid foams. This was a 2-part liquid polyurethane foam. Some of you may be familiar with polyurethane foam that comes in a can, and you can spray it. That requires air to cure. I actually tried using that to make some of these pieces, and even after 24 hours in a mold, they hadn't cured because they don't have any air in the mold, and then I had a big mess to clean up. So then I went and bought some 2-part polyurethane foam, which I mixed, and you can pour it into a closed cavity, and it forms a nice foam structure which you can make in sort of any shape if it's a liquid foam. You do need to make a mold, but it was pretty useful. You can also get all of these foams in a variety of densities depending on what kind of compressive forces you expect on your foam. Higher density, you want the density as low as possible for weight reasons, but you want it higher so that the foam doesn't crush as easily. And if you call up a supplier or manufacturer, they can give you a variety of different densities of these expanded foams. It's pretty convenient. So the urethane foams are much more resistant to many solvents than polystyrenes. So for that reason, they're often used when supporting fuel tanks or things we might think we get structures where there might be some resins that leak, something other than the resin that would leak onto it. Another foam that I passed around was the PVC foam, polyvinyl chloride. This is a bit changed its color because I left it in the sun, but it's generally a little bit darker blue than this. And it can be heat formed a little more easily than the polystyrene foams. One of the things you can do with this foam is to put it in an oven and just above the temperature it begins to become soft, but not so high that it starts to melt, and you can use a vacuum or mechanical pressure to slowly form it down. It's harder than it looks to heat form things. I'm not sure I would really recommend it. This stuff is really easy just to pour, and I think I would prefer that. Other foams that are used in aircraft are the polymethacrylamides. I'm not really sure how to say that. So they called it Robicel. It's sold by a German supplier. It's excellent for sailplanes and low density structural applications. And another type of foam is called syntactic foam, which basically means you mix in little glass spheres into your resin and you make a foam yourself. Nice thing about that is you can make it whatever density you want in small quantities right on the spot as you're doing your construction. And it doesn't, if you're using an epoxy resin, it doesn't expand or contract, so it stays at the exact density that you want. Whereas this has some parts with a little bit higher density, some parts with a little bit lower density, and may not be quite as high strength. Finally, people think wood is that can't be a good material compared to foam, but in fact, balsa, end-grain balsa can have some of the best compressive strength, higher than any of the other foams. It can resist crushing very well. It's also fun to work with. It smells good.
So you were using the polyurethane one?
I was using polyurethane for the carbon fiber pieces, the doubly molded pieces, and I used polystyrene for the red painted structure on the top. And I'll show you how I did the construction, and you'll see why I did that with those two materials. So I actually, this demonstrates almost all of the techniques that I used that I'm presenting today. If you want a material that's a bit higher compressive strength and a bit even stronger than foams, you can use honeycombs. So honeycombs come in a bunch of different materials. You get metal, like this aluminum honeycomb, aramid, like the Nomex honeycomb that I passed around, craft paper even. They have paper honeycombs, mostly used with cardboard and shipping and stuff. I wouldn't really recommend it because if it gets wet, you're in trouble. Loses all its strength. And they have also glass carbon honeycomb structures made of the little fibers, just like the fiber reinforced polymers. You can gently bend these honeycomb structures along a single curve, but you can't do a double curve. You can't bend it on this axis and that axis at the same time. So it's more difficult. You can't really use this for except for very, very large compound curved surfaces. Also be wary of cell defects. Sometimes the honeycomb, the way that it's produced, it will have lines of improperly made cells, and those can become very weak in practice. That'll be it's like when you're making glass, the glass fibers have fewer imperfections, and the smaller your piece of honeycomb, the smaller your imperfections are going to be. You're less likely you're going to run into them. So now we're going to talk about the design aspect of these a little more, and if you guys are going to try to make any carbon fiber or reinforced polymer structures, you might want to consider some of these things as you're doing your design. So unlike metal, where you want to make a lot of little pieces and have them come together to make it easier to build and use bolts, you want to do everything with as few pieces as possible when you're designing carbon fiber or reinforced polymer structures. You don't generally want to use simply curved surfaces. So simply curved surfaces, again, just one bend. You want to use compound curves if you can when you're making these surfaces, because they make much more rigid structures. The compound curved surfaces cannot bend or flex nearly as easily as something that only has a single curve in it, because this can twist. But if this was like a dome structure or half sphere, it's much more difficult to deflect that in practice. You want to avoid compression loads in your thin pieces. That's why we're using cores after all. You don't want to bend your parts like that. You want to have this attached to a core structure so that it doesn't buckle under loading. You don't want to have sharp corners. You want your sharp corners here. Not only are they hard to make, because if you wrap your fabric over the edge of the sharp corner from a foam or something like that, typically you'll have an air bubble that'll form in the corner, or the fabric will pull up. It's really hard to do. It's much easier to create a radius and to form it around the corners. And the same thing here. It's pretty hard to make a sharp T-joint. If this was one piece of carbon fiber that's pre-cured, this is another piece of carbon fiber that's pre-cured, you're going to need to sort of build it up either with some paste or foam or something like that, and then do a few layers of carbon fiber on the outside to bond. We'll talk more about that in a second too. If you can, and if you expect a stress concentration, you want to embed some metal or plastic and machine it later, after the curing, to the precision dimensions that you need, because it's pretty hard when doing this by hand to get a real precise dimension in the material immediately. Also, the real life strength, one of the reasons we're going to do some testing is it's pretty hard to estimate for amateurs because it depends on so many different things. What's the humidity of the day you're doing it? Did you cure it at a low temperature or high temperature? Did you use the right epoxies? So if you want to be certain, build it, break it, and then rebuild it. So more on stress concentrations. as I've said many times, orient the fibers in the direction that you expect the load to go. Don't allow shear loading of the fibers, since the shear strength is often half of the tensile compressive strength. And when you do have something that would be a shear loading, it's often good to orient the fabric at 45 degrees, what's called on the bias in some cases. So if we had if you were imagining making an I-beam out of carbon fiber, and we had, say, a bunch of unidirectional fibers running all in this direction on the top, and a bunch of unidirectional fibers on the bottom, and we made the shear web like this would be shear loading these fibers quite highly and would not be a very good way of doing this. So the better way would be to orient the bidirectional weave of this middle structure here so that they're at 45 degrees, so that when you push here, these fibers become in tension and these fibers become in tension and compression, or however it would be there. And the structure will be much stronger than this one here.
These are 3 plates of carbon fibers. One is vertical and 2 are horizontal. Okay.
This would be a very common structure in one of the early light airplane wing spar designs. So when the strong load-carrying structure in an aircraft wing would have a top spar cap, a bottom spar cap, and a spar web here, which would hold the two structures apart, and this would carry a huge compression load from the entire wing as it's as it's supporting the aircraft, and this would be under tension, and those two structures support the wing of the aircraft. The core material in the sort of beam loading example is undergoing a shear load, and if you're not really familiar with mechanical engineering, you might imagine some sort of truss structure that if you were to support this truss at both sides and apply a load in the center, some of these structures will, some of these rods, I guess, what do you call them, connecting? Some of these connections, beams will be in tension and other ones will be in compression, and if you were to decrease the spacing between these truss members and smaller and smaller and smaller, you get the incremental shear load, or the shear load distributed over the whole core material. So in sort of the continuous case, this becomes something like that. I don't know if that made sense to you, but it made sense in my head. Core materials. So the piece that I showed you that was broken of the carbon fiber and honeycomb should emphasize a couple things here. Core materials must be connected continuously because of the shear loading. You can't just put 2 pieces of foam together but not have them glued and then put fiberglass on top, because that'll become a point at which the shear loading moves the 2 pieces relative to each other, and the fibers on the surface will begin to pull off of the core material, and you have a failure. Once that starts to happen, you can have bending, buckling, and everything starts to fall apart. So glue your foam pieces together, glue your core materials together, and make sure you have a good bond between your core material and your fabric on the top. Problem with core materials is they often crush easily. So add extra layers of fabric. One thing, if this was your material and you expected a point load or some stress concentration to occur there, you can just build up some extra layers of fabric on the inside. You just cut out extra things and put them there. And you can either do it like this or like this. It doesn't really matter, however you want to do it. This can look a bit smoother. This can make it more obvious where you have them, so sometimes you can forget underneath where the exact center is. Never leave the core material exposed to the air. You want to always have a little bevel, if it's a thick core material, a bevel on the edge, so that instead of drilling a hole here, for example, you'd want to bring it down here and drill a hole here just through the fiber reinforced polymer, not through the core material at all. If you were to drill a hole through the core, you would be exposing some of this to the air. It would become easy to pull off the fabric off of the core, and if you had some sort of loading, it's pretty easy to work to wiggle the thing back, the bolts back and forth, and to make the hole bigger, and it's not as good. So let's talk about holes, because we still need to drill holes and mount things in carbon fiber parts. Most amateur fiber reinforced polymers, it's really hard to tap them, to add threads to them very well. If you were to just take a solid piece of carbon fiber, to drill a hole in it and tap it, very often the process of tapping it or screwing the bolt hard will start to pull the fabric apart, and you'll get a little bit of bulge on the top, a little bit of bulge on the bottom, and it won't really be a very strong way of doing that. So this is something you want to avoid, if possible. Another thing you want to avoid is shear loading your bolts in general. This is not quite as fatal as that. Maybe you could put a nut on this side and connect two pieces of carbon fiber like that, as long as this is not cord, as long as this is just a solid piece of carbon fiber. And you could shear load it lightly, but I wouldn't recommend it for stronger joints. A better way to do it, to either glue using structural adhesive a piece of metal, like a little flange or something, to the inside surface to distribute the load of the bolt a little better. Maybe to embed a small piece of metal, particularly for medium stress areas, you can either cut out and just put a huge piece of metal, or maybe a piece of metal with some sawdust, flux, or other things mixed in the resin to help distribute the load from the high stress aluminum metal part, or maybe put a layer of fiberglass or carbon fiber over the metal part that's embedded, try to make sure you don't have air bubbles, and then drill a hole through it. And again, just try to distribute the load whenever possible. For really high stress parts, you can actually make the part from scratch, considering that you want to orient the fibers in the direction of the load. So say we had a bolt like this and a bolt going in here, and we're going to be pulling the two bolts apart really, really hard. What you could do would be to just wrap those two bolts with carbon fiber fabric a bunch of times, and then maybe put it in a vacuum bag, and the vacuum pressure would hold all the fibers together real tightly and cure it in this shape, so that you would have all the fibers running around the bolt. They'd be unbroken, and you'd have about the strongest thing you could make with carbon fiber or an FRP. Cured carbon fiber pieces, cured composite pieces can be joined together. So if you can't make something all at one time, which is the best way to do it, you can make it in smaller pieces and then join the pieces together. And the bonds that you make in this joining two pieces together can be stronger than the original structure. The failure may not actually be at the joint. So you can take a butt joint like this, where you'd have, let's say, core, FRP, and you just sort of add layers of, you clamp the two together, and you would add extra layers of fabric on each side and squish it together and let it dry, and that could be very strong. You could make another butt joint like this. If you want to have it a little more flush, you could cut and trim two pieces with the core material coming together like that, and add a few layers of fiberglass or carbon fiber to the joint there. Oftentimes you'll have a big long seam, and you can just apply sort of carbon fiber tape. They have pre-cut widths of fabric, kind of like this, but maybe half this size, and you can just buy that, and that makes it really easy for doing these types of joints. Go ahead.
If I bend the right one, the right figure,
Yeah.
if I bend in one direction, you can rip off from the materials that you use to bond the two parts. If you bend this direction, is compressing this.
Yeah.
Stuff is, I expect it to be.
What you would want to do would be to add enough layers here so that it might be flush with the top if you're really concerned about it. Or you could add a layer to the outside. And this might be a point where you want it cosmetically beautiful from the outside,
Okay.
and you're trying to bond two things together. Maybe make this lip a bit longer. You could also add a core material across there. If you're worried about this, you could just do that. There's a lot of different ways of doing it. This is just another one.
Okay.
It'll depend on the specific application. You're right, you could bend and break it in different ways. And you would probably also want to fill in this little gap there to be as small as possible and put resin across the gap or fibers if you can. Another way, if you want to make something that you can assemble and disassemble, would be to make a lip on the edge of the skin so that you could attach a bunch of small bolts with washers to take one big piece here, another big piece. Okay. So we're going to talk about the basic wet layup. It's called the wet layup because it is exposed to air. The resin is wet and just sits there, and then it dries and it becomes hard. A vacuum bag layup, which means we put it in a bag, we suck all the air out, and atmospheric pressure will compress the component, the resin and fiber matrix together to make as little resin content as possible. We'll make a moldless layup. We'll describe a moldless layup, which means instead of using a mold as the surface, you use a shaped foam piece directly, so that you don't have to go to all the labor of making a proper mold and then laying up the part on the mold and then pulling it out and doing all this other stuff. So that's a way to build composite parts with not as much work. And finally, I'll talk about the molded pieces and how to make those. So these are some photos. These are going to be pretty similar to what you're going to make tomorrow or the next day. We're going to weigh some resin. This is a 2-part epoxy using a nice scale. All of your fabrics should be pre-cut. You'll have to cut them to the exact size carefully. And essentially all you do is paint the fibers with the epoxy resin. You can wear gloves. We're going to have polynitrile, or I think we're going to have nitrile gloves, which are blue in color, not these latex gloves. And then we're going to have, we're going to use glass surfaces, so that with some waxed glass, you should be able to pull the fiberglass off, or the carbon fiber off, as soon as it's cured. And then you end up with these nice mirror finished parts. So all of these parts here, I think, we laid up on glass. We could also lay them up on any sort of surface. You can do this on any shape you want, as long as you've waxed the surface really well so that you can pull it off. You can also use a non-stick plastic, like this green vinyl. It's commonly used for, I should pass this around too. These are the 4 layers of the vacuum bag technique that we're going to see next. It has a green vacuum bag, which is the sealant, keeps an airtight seal between the part and the atmosphere. There's a bleeder ply, which absorbs extra resin. There's a release ply, which is a pink and has little perforations through it so that the resin can flow through. And then there's a peel ply, which can be attached, or can be against the part if you expect to be doing a multi-step layup. So you would put this peel ply on there, and then you pull it off after it's cured, and it leaves a textured surface. And that textured surface can be better for bonding to. I hope to make that a little more clear. So here we go again. Another type of construction method is to use a vacuum bag. So here you're going to have a flat surface. I've got a gummy tape. It's kind of like clay and rubber mixed together. It's great stuff. It's double-sided. I put a plastic bag over the whole thing, the bagging film. And I've got some PVC foam, some carbon fiber. There's some bleeder ply here. I've added a big space between here so that if any extra resin starts to flow this way, it's going to get absorbed by the bleeder ply and not going to go up my tube into my vacuum pump and get resin on the inside of my vacuum pump, because that would be very bad. Better ideas are to use a bypass, so like a bucket, that the bucket will also take a vacuum, and if any resin does flow up that tube, it goes into the bucket. It doesn't go to your vacuum pump. But for the scale of stuff I was doing here, I could get away with not using a bypass. I could just make sure that my resin stayed over there and didn't get sucked up in the tube.
So did you use this technique for your stuff?
I did use this technique
Not the wet one.
I used both the wet technique. I used the wet technique for this, and I used the vacuum for the molded pieces. So here we can see I had about 0.8 or 0.9 in an atmosphere. I could not get all the holes out of the plastic bag, so really, really surprisingly difficult, even for a small thing, to get a completely airtight seal. It's also difficult to do this technique because you have very limited time. The resins and the epoxies that we're going to use will start to become gummy after about 30 to 45 minutes. Their viscosity increases a lot, and when their viscosity increases, you can't use them to wet the fibers out anymore. They just, your work time is over. Just work quickly because you've got 30, 45 minutes depending on temperature. On a cool day, you might have 45. On a hot day, you might have 20. And that depends on the resin and the data sheet that's provided from the manufacturer. Anyway, you can see here, if you look carefully, actually, I hope you can see here, that there's little dots as the resin has seeped through the perforated pink film. So the part itself there's the tool, the shape that you want to form. Then there's the stack of carbon fiber, which you wet out with the resin. Then there's a peel ply if you want, or a release film. Then there's the bleeder, that white stuff that absorbs extra resin. Another layer of release film, I guess, or another layer of breather fabric, which lets the air flow through this fabric and to your pump as you create the vacuum. I just used a lot of the bleeder ply on top to make sure that there was plenty of space to both absorb resin and provide a path for the air to escape from the vacuum bag. And the third way to do it is to do moldless composite construction. So these are photos of the body of the robot when I was constructing it. It's pretty pictorial. I took 3 pieces of polystyrene foam. I glued them together with an adhesive spray foam, although I think it would have been better to use a slightly stronger glue because it would be better to use a stronger glue, but you still have to use a glue that you can cut with a hot wire, as is shown here. So after I glued those 3 pieces together, I nailed into the side an aluminum form with little markings on it, cut with the markings about every 1 or 2 centimeters. And then Traveler helped me out. We went around and using a hot wire with a nichrome or stainless steel wire stretched between 2 things, between two boards, we gently pushed the hot wire against the aluminum metal form and gradually traced our way around the metal form. This cuts the styrofoam foam, and you can make these great curved surfaces in 1 step. And you just go through counting off the numbers, it's like 21, 22, 23, so that you and your partner are going at the same speed as you go around. There's another one of these on the other side. We'll do this tomorrow. If you want, we can try cutting some foam pieces. You can get a little experience of making things directly out of foam. Then I put some fiberglass on it, and I vacuum bagged it, and I ended up with this after trimming. Actually, the fiberglass went beyond this point, but I just trimmed off the edge. Because the next step, I added an inner form, and I cut out the inside in the same sort of way that I did the first one, using the hot wire. Then I glued on a piece of foam onto the open side to make sort of an open box. And then I sanded the edges, just directly shaping the foam, and applied fiberglass to the outside of that. I wasn't able to vacuum bag it in this step, like I did in the first one, so this is not quite as nice a finish. And then the inside, you do the same thing. You turn it around. This is the same thing seen from the other side after the fiberglass, and it shows that in the inside I can then apply fiberglass to the inside and make a nice composite box structure.
How did you heat up the wire?
I heated up the wire electrically. I passed about 5 amps of current. 3 to 5 amps, I don't remember exactly. Depends on the length of the wire and the thickness.
How did you make the aluminum form?
I drew drew the shape I wanted. I printed it out life size with a printer. I used a marker, traced out the shape I wanted, and then I used some tin snips or some sheet metal cutters, and just work carefully. And if you do two of them together and then you bolt them together and you sand the edges or use a file, you can get a consistent shape across both of them. And you use a level table and you make sure that they're not twisted. Sorry. You make sure they're perfectly aligned with each other, so when you stretch the hot wire across, you're not skewed in any way. If you want to skew it, you could. You could make a shape that was a little more unusual. You could use two different shapes. You could make a cone, I suppose. You could fix one end and then move this in a circle and stretch that cutting wire. You can make all kinds of weird shapes, as long as you can cut it with just one straight line. And finally, the doubly molded composite sandwich parts, which were the most difficult to make and most time consuming. So first I designed the shapes that I wanted on the computer. I printed out the molds. I printed them out very thin. In fact, you can see this is not really very strong. This were printed with the 3D printing prototype, and I glued them together. I actually used a bit of fiberglass on the inside to make it reinforced. I ripped off this was used as the inner mold. So this was the call plate or inner mold that I used. And the outer mold, it's not in good shape right now, but it looks like this. What I did was glued these pieces together on a flat board, covered it with some Bondo, as you can see here. So this was covered with a polyester body filling putty, which you can buy at any hardware store, and it makes it very easy to sand and nice surface. I then painted it black with gloss black. Glossy black shows all your mistakes more easily than a white color. Glossy black lets you realize how many mistakes you made doing this. The reason I added the Bondo was because the surface you get straight out of the printer has lots of little irregularities, and I needed something to fill in those little gaps more smoothly. You end up with a stair-step effect. So I filled it in with the resin and then just sanded it lightly. It took a couple hours. Then I lay the carbon fiber fabric on the inside of that mold after waxing it 5 times. Wax it as much as you can. If you think you waxed it enough, wax it once more. Lay the carbon fiber on the inside. Vacuum bag it. This is a different piece. I'm sorry, I don't have a photo of this being vacuum bagged. Different piece. And this is a different piece again, but this is what happens when you pull the fiberglass or the carbon fiber out of the mold. You already have a nice, smooth, formed piece in the shape you want, but it's still not totally rigid yet because there's no core. This was only like 3 or 4 layers of fabric. Then I have an inner mold. In this case, it was something like this. It would go on the inside, and I put this back in the first mold and cover it and fill the gap between the outer surface and the inner surface with expanding foam. If you pull that off 24 hours later or 6 hours later, however long it takes for the foam to dry, you have the inner surface of the fiberglass, and I then applied the inner surface of the part that you want, and I apply carbon fiber to that surface, and you end up with a finished part, which weighed 170 grams or something like that. So I had a really stiff, strong foot. This whole process takes a couple of weeks because each step requires that you wait a few hours. When you print these out, it takes a few days. When you do the bondoing, that takes about a day to do. When you apply the paint, you gotta maybe paint one day and wait for the paint to dry. Please wait for the paint to dry. When you wax, you have to wait 24 hours after you wax so that the wax is really hard. When you do this and you do the vacuum bag, that takes a day. So it's not a very fast process, but you can do this here with very few tools. This doesn't require anything except a little bit of patience and some sandpaper and a rapid prototyping machine. Yes, you can make the mold out of anything you want. Some people make them out of putties, plaster of Paris, foam, you can make foam and fiberglass just to make a mold if you're going to be doing a lot of them. And if you take nice care of your mold, unlike what I did, you can make a lot of parts once you have the mold, as long as you're waxing everything well.
You need to re-wax every time.
I don't know. I would say that the first time you're going to need to wax a lot, and maybe the second or third time you're going to need to wax. I didn't have a proper molding and tooling wax. They have some very nice hard waxes you can buy that once you do that, you do not need to wax them every time. Once you've released 3 or 4 parts from a mold, I believe you do not need to wax every time, but don't quote me on that. It's not something I'm familiar with. The professional guys have some way of doing it where they don't need to wax every time. They can do a couple hundred parts between waxing.
Ivor,
Yeah.
can you use the ABS plastics, the one coming out from the 3D printer, as a core material?
Good question. You could. I thought about this. The disadvantage with making your core material out of ABS plastic is that it's very heavy. The ABS plastic is the heaviest thing there. And if you're making a really high stress part, yeah, I can see that.
So you can.
And the other disadvantage is when you're making something like this, where I've made an exterior mold, the exterior surface comes out shiny and ready. When you do things like the previous slide, like this, you end up with a rough surface. You end up with a textured cloth surface on the outside. And that requires, you can even see it if you guys want to come up and look at this later, on this surface here. This red piece has a bit of a cloth texture to it. Now I didn't add much paint because I didn't want to add a lot of weight, and I didn't add much extra resin. But you end up with something, the surface is not as nice. Maybe that's fine, maybe you can just add more paint. But I haven't found a good way to make a part with an ABS plastic core.
Yeah, because I was thinking, okay, you just designed the part, you print it,
Yeah.
reinforce with the little.
Yeah. I tried printing ABS plastic honeycomb. I thought that would be kind of cool. And that might work, but it's a bit tricky also. It's not strong in the right direction when you print it up usually. Because you would want the fibers of the honeycomb, if the cell is open this way, you want the fibers going this way, I believe. And if you're printing it up, you're making layers like that. I don't think it would be, it might work, but it's also not as light as you expect. Like if you compare that to this is nothing.
Otherwise, it
Yeah.
doesn't work.
Yeah.
If you just leave, I don't know, half a millimeter
Yeah.
thickness, it doesn't work.
I was just going to say that it would be very difficult to make the whole part nearly as light as just like aluminum with some bolts in it.
Yeah. Yeah.
Because that doesn't really have any real volume.
Yeah. Now, maybe there's a way to do it, and you guys can tell me when you figure that out, because that'd be cool. It'd be great to be able to print out cores or shapes or molds directly. This process is essentially we're printing out the mold, and then we're making the surface of the mold a little nicer so we can produce parts with beautiful surface finish immediately. Otherwise, you have to do a lot of sanding, and that's a lot of work. Now we'll get into a few more construction details. So clean surfaces are important when you're actually building stuff. Keep your table, your fabric, your mold free of dust when you can. When you're making a mold, make it as perfect as you can, because any imperfection on that will become an imperfection in your part. Everybody says this, but nobody believes it, including me. Spend 90% of your time doing preparation, only 10% on the actual layup. Because you're going to spend 500% of your time sanding and repairing. I'm not a very good workman, and when I do these parts, I end up spending a lot of time sanding, repairing, whatever, when I knew I should have just gone back and done it right the first time. It's really hard to resist the temptation to rush to the part where you put the fiberglass on and put the resin on. So you only have 30 minutes, roughly, when you start mixing these room temperature epoxies before they start to harden. So make sure your fabric is cut, make sure everything is ready before you mix anything. That's the last thing you do. And then once you do the 30 minutes are up, you immediately clean out, and you can't do anything else on the part usually for the next 4 to 6 hours at least. So that's kind of like the last thing you do each day, is do your layup and clean up and go home. So the temperature is important for doing these room temperature epoxies. It should be between 15 and 30 degrees. The hotter it is, the less time you have to work, but on the other hand, the stronger the part may be, because the resin the A molecules and B molecules will bind together more completely. Working in direct sunlight on a hot day can be surprising. I've had resin cure in less than 10 minutes after mixing on a hot day in full sunlight. Humidity should be less than 50%. So the best places are like in the desert, or they have humidity controllers. Here in Genova, we can't do anything about this. So we're going to have a layup tomorrow, and it's going to be like 80% humidity, and whatever. The reason you want the humidity low is when you put a vacuum bag around it, for example, the moisture will become a gas again. Any water absorbed by your resin will gas off as the pressure drops to near zero. The boiling temperature of water will become above that, and you get the water boiling off, and that creates bubbles in your epoxy, and it looks bad, and it decreases your strength. More rules of thumb. So you want to wet out the fibers as much as you can with the resin, but you want to have as little resin as possible, so low viscosity helps. Sometimes there are additives you can add to your resin to make the viscosity lower. You can also use a heat gun to apply extra heat to a specific area that you're working on, and the hotter it is, generally the less viscous the resin is. On a hot day, the resin penetrates things more easily. So air bubbles are bad, as I just said, both cosmetically, because they have little holes in your structure. You notice that a lot of these, if you look at the surface, there's tiny little pinholes on them. It's too bad. I didn't know how to get rid of them. Go ahead.
Is there a limit to the number of layers of fiber you can do at once? Like you do 3, 4, 5?
Generally, there's no limit on the stacking you can do at once. You could do 20 layers at a time, but what you do is you pour resin or mix resin into usually no more than about 3 layers, because you can't usually do 3 layers at a time, and then you brush it out, or you use a squeegee tool to press the resin in, and then you add 3 more layers of fabric, and you do more resin, and you got to resin. And you can do as many as you want, but you have to do it pretty quick. You can't, if you're going to vacuum bag the whole thing, you want everything to happen in a few minutes. So we're not going to do more than, I think, 6 or 8 layers in the little pieces you're going to do. You're going to make little samples about this big, and we'll get to that in a second. We're doing on time. I think we'll do just fine. So it's very useful to have a partner when you're doing this. So one person can keep their hands clean, one person can keep their hands, maybe get one hand in the resin, because quite often you want to kind of just hold it or adjust it while you're trying to paint it out, and you might get one hand with some resin on it. And if you've got a gloved hand, that's totally fine. It's almost inevitable in some ways. But don't get both your hands full of resin, because then you can't take your gloves off very well, and you can't touch anything. And if you drop something or you touch yourself accidentally, yeah, it's bad. If you're doing layups in air, a lot of times the epoxy will have what's called an amine blush, I believe, which means after it's dry, there will be like kind of a waxy surface on the resin, and you need to wipe that off with some soap and water or some acetone, I think. I'm not actually sure what the proper chemical is, to make sure that the wax is gone from the surface, so that you're bonding again directly to the epoxy or to the carbon fiber. And also, if you're doing multiple steps, if you're going to do, if I was going to bond something to the surface of this, for example, this cured piece, I should have added a peel ply, which is that nylon white plastic, to the outside, and brushed that in just as if it were another layer of carbon fiber, so that when I pull that off, I would have a rough surface to bond to. If you look at this, you may notice that this, in the center, uses just plastic and is quite, somebody did have that. This is smooth because it had a plastic surface against that, And this on the edge, look at you smiling. Okay. And on the edge here is where I applied the peel ply, so it has a rough texture. So it'll be much easier for us to add another layer of carbon fiber to this rough surface than it would be to this, which is smooth. You get a better mechanical bond. Well, you can look at that if you want. Vacuum bagging rules of thumb: don't let resin flow into the pump. Make the bag bigger than you need it. It's amazing how often you can tear the vacuum bag as it begins to find every tiny little crack in your mold, and it begins to press tight against the piece. I've tried using a bunch of different tapes, but the best is the gummy tape that they sell exactly for this purpose. Duct tape, air goes through it. Scotch tape, air goes through it. Electrical tape, air goes through it. It's really hard to make a nice seal.
By that's mean like a little cup with that's air.
Yeah, it'd be if this was a cup and it was, you have a cork or something going in the top. You have your vacuum pump tube coming in, it goes in, and then you have another one coming out like that, so that if any resin comes in this tube, it'll get stuck in the pot and it won't go to the.
Can we buy one of those? Or?
Yeah, we can buy one or make one. We won't be dealing with so much resin that that's a problem for us. But if you're making a part or you really want to put a lot of resin on it, you should be careful to make sure that it doesn't go up your tube.
As long as, how many pumps do we have?
We have one crappy little pump that I have. And it's even the wrong voltage, it's an American voltage. It's 110 volts. We have to have a transformer there. It's terrible. This was all hacked together like 3 years ago when I first got here. We just bought whatever we could find. So, other things.
Have a nice vacuum cleaner, pretty strong.
Vacuum cleaners usually can't pull more than about 20 or 30% of an atmosphere. You can use those Venturis, but those are not great either. I mean, the best way is to use one of those piston vacuum pumps that are designed for the purpose. They can get 90% vacuum or something like that, or maybe more if you have a really good seal.
And the current one, what is it?
It's a proper oilless. It's a proper oilless vacuum pump. Yeah. So cutting and drilling. You can cut thin pieces, maybe up to about 4 layers of fiberglass or carbon fiber with a sharp knife, and that makes very little dust. And that's what we're going to do. It's a little difficult, but you guys get to do that, not me. So great. Hacksaws can be used. They produce a little bit of dust, which you need to clean up. You can drill carbon fiber and Kevlar just fine. If you're drilling really fast, you can set the plastic resin matrix on fire because it insulates heat pretty well. But that's unlikely at the speeds you're going to be doing. And if you have a sharp bit, you can cut through it faster. It shouldn't be a problem. Dremel tools with a little abrasive wheel are really great and probably the most useful thing for cutting this because typically you're working with unusually curved surfaces and it's hard to cut it in another way. But a Dremel tool by hand, you can actually, working slowly, you can be pretty accurate. Flat pieces can cut jigsaws. You can cut with a jigsaw, a table saw, a bandsaw, whatever you want. So again, please always wear a dust mask. Clean up your dust immediately using a water filtered vacuum. Shop vacuums aren't good enough, as we discovered. And change your clothes afterwards so the dust doesn't spread around. This would be on Thursday that we'll be making any dust. And we're not going to actually do any real sanding. As I said, we're just going to cut with a knife so we don't make dust. This was what I was trying to describe unsuccessfully earlier about how we can cut and shape foam cores. So I'll just go down the list. So we can use knives for cutting foam, works pretty well actually. Jigsaws are always fine. Foam dust is not particularly dangerous. It's easy to clean up. Heat forming with foam is pretty hard actually because the foam is a good insulator, so you need to have the whole atmosphere that you're doing your heat forming in heated to the right temperature. You can use an oven for this if you want, and maybe, or a small like toaster microwave thing might work too if it's a really small part. But it's pretty hard to do. I was disappointed. I tried several times to heat form and I'm not very good at it. I don't have the right tools. Expanding foams are what I used for the really complicated parts. Polystyrene foams not urethane foams. Polystyrene foams can be cut with a hot wire. Go about 1 centimeter per second and don't stop for any reason, so make sure you can do it all in one smooth motion. If you stop, this piece was cut with hot wire. You can see the little spider webs coming off it. That means that you're cutting at the right temperature. If you're burning it or you're not seeing the spider webs, your wire is not hot enough. And you also need to bevel the edges, as I mentioned earlier, so that there's no big sharp edges. You step it down. You can use something like this little drawing here to cut the foam. Basically, you take 3 boards and make a nice 90-degree angle there rigidly. You add a bolt through here and use a turnbuckle and some wire to tension this 9-chrome or stainless steel wire quite tight. When you heat it up, it will generally stretch a little bit, which means you then need to retighten it a little bit. Not too much, you don't want to break it, but you know, guitar string tightness is about right. And you put a few amps of current through it. Start low, practice cutting on a few small pieces of foam, and then increase the temperature as you need. Yeah. So finishing FRBs, what I mean by finishing is the surface finish for painting and stuff like that. Boat builders usually put a real thick layer of resin directly on the mold, so that the outside surface has a real thick layer of resin. It's easy to sand, you can make it really smooth, it's great. And it's a great thing to do if you can tolerate the extra weight. Everyone in manufacturing mass parts that aren't in the aeronautics industry does this. But remember, that surface is just weak resin, it's just adding extra weight. If you're in aerospace, if you're making spacecraft or maybe really high precision robots or something like that, you wouldn't want the gel coat. You want to add the minimum amount of resin that you actually need. You also want your thinnest fabrics. You want the carbon fibers come in different thicknesses and fabrics and everything like that. You want the thinnest ones on the outside that is closest to the mold, because thicker fabrics have more up and down that you're going to have to fill in later, and you want to have a more visible texture when you finish your project. So you'll have a smoother surface if you use a very lightweight cloth directly on the tool, and then as you get further away from the mold, you can add thicker and thicker layers of fiberglass, which means you have less work to do because you can add one big thick layer of fiberglass instead of 3 really thin layers of fiberglass. And it can save you some work. Kevlar, this yellow stuff, cannot be sanded very well at all. It's very hard. If we were to try to sand the edge of this, what would happen is we would gradually eat away at the resin, and the fibers would happily just bend away, and so you'd have sort of this yellow tennis ball fuzz on the edge. You can cut with a sharp knife, but it's really hard to sand. Some people say you can like apply super glue to the fuzzy stuff and then kind of cut that off with a knife, but generally, if you're trying to sand Kevlar, you've done something wrong. If you want to sand to Kevlar, add fiberglass or something to the outside. Fiberglass is almost transparent, especially a thin layer. You can apply fiberglass over Kevlar to provide a nice surface for finishing. And you can sand fiberglass and carbon fiber. It's hard work, but you can do it. You should also make sure that the paint that you use matches the chemistry of the resin. And you can even add tinted, like chalk-like substances to your resin if you want to give the product a different color. So you can add red or white or blue pigments to your resin. So this will be some more rules of thumb, I guess, for tomorrow's layup. Make sure your fabric is ready before you start. Try not to mix air into the resin when you're mixing it in your cup. It's surprisingly hard not to do that. I mean, if you do it, it won't kill anyone. It doesn't kill anyone, but it does make your part have little bubbles in it, and it looks less pretty. Pour the resin onto the mold first and brush it out. So before you lay your fiberglass on, if you do the fibers first and then put the resin on, sometimes you'll have little air bubbles right against the surface. You always work from the center outwards, so you pour your resin in the center and you work outwards. You always adjust your fabric from the center outwards. If you go from the out to the inside, you end up with a big bubble in the center, and it's not good. One of the things we're going to do tomorrow is we're going to have a glass surface you're going to work on. You're going to put your resin down. You're going to put your fabric. You're going to wet out the fabric. Then you're going to put, you might want to put a layer of plastic that doesn't stick to anything on it, and then carefully squeeze away all the extra resin with that, and then pull the plastic back off of it, and leave a nice part with no extra resin on it. People who are doing vacuum bagging don't need to worry about that. We're going to have enough, we'll have a space, we're going to have, I think, 8 or 10 groups maybe, of 2. And 4 of you will get to use the vacuum bag equipment at the end, and the other 4 groups will have to do it air style, and we'll compare how much of an improvement the actual vacuum bagging is. It's too hard to wet out more than 3 layers of fabric at a time, so do a couple layers, especially for carbon fiber, which you can't see through. You can tell with fiberglass if you've added enough resin because it becomes transparent. But with carbon fiber, you maybe can't tell that you haven't added enough resin. It's more difficult, so you want to do maybe just 2 layers, or 3 if you're feeling great. If you use tons of resin, you don't have to worry about making sure you got it. And finally, after the resin starts to cure, you should let it sit for 4 to 6 hours before touching it. After 6 hours, it's called the green cure stage. It's still a little soft, and you can often cut it with scissors. It's kind of a nice time to trim if you're around. Other notes?
So you don't put more than 2 layers. Yeah, I thought you have to put 1 layer, then again the resin, and then another layer. Each layer
you can do 2 layers and then pour resin, 2 layers and then pour resin, or maybe 3 layers if it's fiberglass and you can easily see it. 3 layers, pour resin, 3 layers, pour resin, and brush it.